Yeah, we'll just wait a couple more minutes for people to join. So I just launched a poll. Can people, it's just to get a sense of how people are feeling about the material. So if you have been following the exercises, indicate yes. If you have been struggling a little bit, indicate no, and I'll calibrate depending on what the responses are like. 60-40, about there. So for people who are who haven't been following the exercises, and those who have also have been following the exercises, if people could just post, sort of the stuff that has been confusing, just paste it in the chat so I could get a sense. Or like which part is confusing. Is it the coding exercises? Is it the higher level concepts? So can you just give me a sense by the chat what is clear, what is not clear? Would be helpful. Coding exercises. Connection between the theory and the Python scripts. All right. Coding exercises. Coding. So yeah, seems that like the coding is the people at least seem to be understanding the concepts, which I think is good. But the coding seems to be a little difficult, and that is I don't want anyone to feel sort of unsettled, like learning a new sort of framework just out of the box is not an easy thing. So, but I will try to go through the coding exercises a little more slowly, and we could then sort of like walk it through together, as we sort of do this class. So I'm gonna I'm going to quickly go through the concepts for today, and then we would try to do more coding exercises today, to sort of, and I'll try to show you side by side the theory and the coding so that you can see the correlation a little bit better. All right, so let me share my screen. But thank you all for sharing the feedback and sort of that sort of perspective, because it's good as I sort of calibrate the class for the remaining few. So yeah, let me share my screen. All right. So let's do a recap again on some of the concepts, because just seeing these concepts over and over, and I think will be helpful. So let me pull up the coding exercises as well as I go through the recap. Give me one sec. All right. All right. So to get a sense, all right, so let's go over again the concepts. So we're trying to learn about deep learning, and as we said, deep learning is a branch of artificial intelligence that is particularly tasked with how do you extract patterns directly from the data in of itself. And as we mentioned, the fundamental building block of a neural network is the multi-layer, is the perceptron. And fundamentally what a perceptron does is that it takes some input, which is x1, x2, and x3. It weights the input and then applies a nonlinearity. Yeah, with regard to people with regards to the coding exercise for today, we're just looking at the day one coding exercise, and I'll post today's coding exercise once we tackle it a little later. So the fundamental thing that, so a good analogy that someone gave me recently, and I think it's a good one, is that, for example, if you're looking to say like fly, say like you're looking to like ride a bike, right? Like you're looking to ride a bike. The first time you ride a bike, you pedal, then you fall off, then you figure out, oh, I need to pedal this quickly, or I need to weight my body this quickly. So you then take the feedback of falling down, and then you go back on the bike again, and you take that feedback, and then you sort of factor in that. You start to ride a little better, and then eventually, if you fall long enough, you eventually learn how to ride a bike. So this is how networks function, is that you have some, in this case, the aspect of falling down on a bike is sort of the data. You get this data point, and then based on the feedback of this data point and how you respond to this data point, you sort of improve your performance. So fundamentally, on a high level, what these neural networks are doing is that it takes some data, right? And it takes some input data. This is the data x1. It passes it through the model, and it makes a prediction. In this case, it's 0.1. In this case, say it fell off the bike. And ideally, you want to stay on the bike. So the actual thing that you want to happen is that you want to stay on the bike. So you have a difference between what is you're currently happening and what is supposed to happen. And then based on that feedback, you want to improve. And that is what we call backpropagation. So in the case of humans, we get these sort of improvement signals, say by falling off of a bike. The only way that a neural network figures out what it's doing wrong is through gradients. And the gradient basically tells the neural network in which direction it needs to move to decrease its loss. And the loss is a training signal that it uses to figure out how badly it is performing. So as you were looking at this before, we start somewhere on the loss curve and you want to get to the bottom. It gets a gradient which tells it which direction to go. And then it keeps on following the gradient until it reaches the minimum loss. So that is essentially how it is set up in PyTorch. So you have a data, you have your model, and the model makes some prediction. So how I've defined the steps in these notebooks is in a very discrete steps. So the first one is to do what we call is to create a data set, because the neural network needs to take in some data for it to for it to understand the data. So it needs to take in the data, right? So I do expect some level of familiarity with Python or programming in another language. So this is a class, and this is how the class is about this data set called MNIST, which is a data set of handwritten digits, and it's of type data set. For people who are raising hands, if you have a question, just post it in the chat. It would be much easier. And the main point of a data set is to sort of basically provide data to the model. So in this case, we want to provide images to the model, and we want to provide the corresponding label, right? So to get the images, we have to first download the data set, which is what these lines do. It downloads the data set and then unzips it. And essentially, it goes through all of the files in the data set and stores it into a list. It stores the file name as well as its corresponding label, right? And then what the get item does is that it gets the list of image. It takes an index, which basically it indexes into a particular position in the list. And you also get its corresponding label because it's at the same index. And then here you open the image. So image.open is a way to actually load the image from disk into computer memory. And then we return the image as well as the label. Does that make sense? If it makes sense, type yes. If it doesn't make sense, say no in the chat and explain no if you don't understand the part. Sweet. Seems generally that people are getting a hang of it. So the main thing is that for any data set is that you want to define how to give the data to the model. That's all the data set is designed to allow you to accomplish. And that means you have to load the image, and you also want to return ideally a label so that the model knows what label to associate with an image. So the get item defines how to sort of index into particular. So what is the values are in the label? So in this case, the label would be the number itself. So for example, the label for this digit is the label 0. The label for this digit, for this image, so this is the image. This is a 28 by 28 image. This is the image that we load in, and the corresponding label is 4, right? And that's all the get item. The most important function in the dataset class is the get item, which basically returns the data in the format you want. And in this case, because we want to classify an image, we want to return the image. We want to return the image and its corresponding label. There are convenient libraries that does this dataset pre-processing for you, but in this case, we've manually defined it, right? So this is the data that is going to go into the model. So now we need, so last part of a data set is that we need to be able to iterate the data set. And iterate means that we are looping over the data set. So it takes in so we have a thing called a data loader. So there's two main things you need to understand for dealing with data in PyTorch is you have a data set which defines how you retrieve just one particular piece of data, and that is specified by the get item, and then you need data loader to iterate over a ton of images or a ton of data points at a time. So you specify what we call a data loader, which takes in a data set, and a batch size, which specifies how much images or how much data points you want to look at any point in time. And yes, the purpose of this program is to recognize handwritten numbers. So we have a data loader for both the training set as well as for the testing set. Yep. And here we just visualize it. This is nothing too important in the grand scheme of things. This is just a visualized data set. So the second part is that we need a model, right? So in most programs, you need the data, you need to process the data, then you need a model. In this case, we look at this, right? So it's very similar. So you have your input layer, which is who has a number of units equal to the number of units of the input, which in this case is 28 by 28 image, which is 784. And then we can define how many hidden layers we want, how many units we want. In this case, we're keeping it very simple. So we just have a hidden layer of size 1000. And then we need to have an output layer corresponding to the number of outputs that we want. In this case, we want a probability for each of the numbers. So we have 10 outputs. Does that make sense? So how we do that is we define a neural network model. And that's, so you see here, this is a data set. And then this is a NN module, which is what all data sets, which is what all models are subclass of. And in the init function, you just define the layers that you want. So they're like the main layers that you care about for this linear layer, which specifies the number of input units and then the number of output units. So here, the number of input units is 2. So for this layer, the number of input units is 2. The number of output units is 3. For this layer, the number of input units is 3. The number of output units is 1. So here, for this one, the number of input units is 784. The number of output units is 1000. Then for this layer, the number of input units is 1000, and the number of output units is 10, which is basically simply put here. And as we recall, we need the nonlinearity function. And then the forward pass just describes how we want to configure these layers to give us the output. So if in this diagram, we have our input X, this is the input into the model X, we flatten it, meaning that we take the spatial image and then we flatten it into a set of units, and then we apply layer 1, we apply the nonlinearity. So what is the hidden layer? So a neural network is composed of layers. A hidden layer just means that it's a layer that we do not observe. So in this case, the input layer is the input, so we actually see the input. the output layer is what the neural network outputs, so we can actually see its output. But what happens in the middle, we don't directly see, so we call it a hidden layer. And for most so what is essentially happening here is a matrix multiplication. So let me for people who are familiar with matrices, your input X is batch size, say 64, and then it is 728, dimension 748. Then you have a weight matrix W1. So remember when we were looking at this here, we have a weight matrix for each input, right? So in this case, we have the weight matrix for layer 1 is it takes in 784. So for each X value, it's 748 units. It multiplies it by 748. And that gives you 1 unit. And then you do that 1,000 times to give you 64 by 1,000. And then given that, it projects it into a 10-dimensional space. So some maturity in terms of being able to understand matrix and matrix multiplication is helpful. In this case, what's basically happening here is just when you take an input X and you apply a layer, it just does a matrix multiplication. And similarly here, and then it applies the ReLU function, and then it returns the output. So this is the most important part. One of the most important parts is how to create a model. Can people post in the chat whether this makes sense or what is confusing, or if it doesn't correlate with what we're seeing on the theory side? So someone asked, how do you know the hidden layer is 1,000? So this is what we call a hyperparameter. This is what we set. So in this case, we could set it to anything we want. I could set the hidden layer size to 45. And at this point, this must also be 45. I could set it to 2,500. And this would also have to be 2,500. So the configuration of the neural network is something that you control, and a skill is designing neural to give best performance. But on a high level, just getting the concepts of a layer being an input, output, input, output, and you specify these values, right? Then we move it to GPU because we've defined the device above. And so so the hidden layer is something that we must set. It does affect the performance of the model. The more units you have is the more what we call capacity of the model, meaning that it has more weight, so it could store more information. But the problem with that is that if you just store all of the information in your training set, it mightn't generalize the testing data well. So it's like, for example, if you use up all of your mental capacity to study the like 10 homework exams, 10 homework problems that the teacher gave you, and you didn't use any mental capacity to do any other problems, you just only learn the specifics of the homework and nothing else. That is sort of the trade-off. So even though you can have a more complex model by adding more units, there is a problem of overfitting. Yeah, so Python does all of the math. So like in this case, normally you would have to do all the matrix multiplications. In this case, it just abstracts it behind this convenient function nn.linear, and it takes an input and output, and it does the matrix multiplication for you, and does it on GPU. So that's the beauty of PyTorch, is that if you would have to come to write this yourself, you'd actually have to define all of the matrix multiplications. In this case, you have to define your input, your output, your input, your output. The next part is the loss function. As you said, this, so after the model gives you your output, here, this is the X it returns, it has to compare itself to what is actually true, or what is the ground truth, or what is the correct answer. So your loss function quantifies the difference between the output that the model gives you and the correct output. And then the optimizer is then used to update the parameters of the model. So for people, so this is, so remember when we looked at this here. So we have a loss. So yes, so this part here where we update, so we compute the gradient. Remember, the gradient is like, even though it looks confusing, it's on a high level, it's very simple. It just tells you what, it gives you a signal of what you, of which direction to go to do better. It's like if you fall off a bike, a gradient would be like the ground telling you, you should not fall on me, you should stay on the bike. So the gradient is basically the signal that the model uses. And then you have to update your weights, factor in the signal. So you have to take the opposite to the gradient, because the gradient tells you what you should be doing. It tells you in the positive direction. You want to know what's happening, and then you want to go down, you don't want to go up. So that's why you have to update your weights in a negative direction to the gradient. So that's what the optimizer is. And you have to set your learning rate. So your learning rate is this value here, and it tells you how confident you want to trust your gradient. Because recall that if the learning rate is too high, you oscillate, right? You just keep jumping around. If it's too small, it takes forever, but eventually, if it's just right, it decreases gracefully. And people who worried about local minima, so this here is a minima, and in this case, it's both the local and the global minimum. In, for example, complex loss functions like these, you have multiple minima. This one would be the global minima, while these would be local minima. You could get stuck in these, and that's, in this case, fine. But it's such a complex landscape that getting stuck in a local minima is usually not too bad. And that's the importance of choosing the optimization function and the learning rate and certain other hyperparameters, is that you could sort of avoid local minima if you choose these parameters correctly. I cannot go into all of the details on that because it's non-trivial, but on a high level, you want to pick your optimizer. In this case, we use a standard stochastic gradient descent. And then the last thing you have to do, so let's look at this again, right? It's for the most part pretty boilerplate. You create your data set, right? You define your model. You define a loss function. You then which tells you how to compare the output of the model with the neural network. You define your optimizer. And then you have to actually train the model. And as we said, training the model is essentially updating it's like you have it has to make some predictions, it has to learn what it's doing wrong, and it updates the weights. It's right. And the flow is very simple. You get your data loader gives you a batch of data and the labels. You add it to the GPU. You pass the data. So remember the model takes in input X. You pass in the data, and the model gives you some output. So this is the model's prediction. This is the output. Then you need to quantify the difference between what the model predicted, which is the output, and then what is actually the correct answer, which the loss function tells you. And then you use the loss that backward to calculate the gradient, Recall that the gradient is the training signal that tells the model what to do, which direction to go. And then you actually update the weights of the model. So look at it. The algorithm is pretty much here. Look how this matches up pretty much directly. So you compute the gradient. This is where we compute the gradient. We update the weights, right? And we keep looping and doing that. So this is a loop, and you loop through the entire data, and loop through the entire data multiple times. So this is how many times you want to go through the data, and this is going through the data. Sense, and here we run it for 5 epochs. You want the loss. You want the loss to decrease, and you want the accuracy to increase. Does this make sense? Please post in the chat if this is clear or not. Perfect. People seem to be getting it. This is great. So what we're going to look at today is another type of neural network called a convolutional neural network. And even though the different layers are slightly different, it's the same sort of workflow. You create the data, you create your data, you create your model, you define a loss function, you define an optimizer, and then you define how to train your model. Which to train a model, all that happens is you get the data, pass it through the model, calculate the difference between what the model predicted and what the correct output is. You update the parameters, and then you keep just doing that. It's like you ride a bike, you fall off, you figure out what you did wrong, you go back on the bike. You ride a bike, you fall off, you figure out what you did wrong, go back on the bike. And that's basically on a high level what is happening. And even though some people who do not have to say, have a program before as much, or the nitty-gritty of the coding is not that important, I'm trying to sort of stress. It's like for people who have a more coding background, they could probably get the coding a lot more easier. For people who do not have it, do not worry. The main important thing is to get the higher level understanding of what is happening. And then you have to spend a little bit of extra time getting used to all of the syntax of Python and PyTorch, but a lot of great resources online. But the key thing is to understand on a high level what is happening. Get the data, pass it through the model, calculate the loss, update the weights, and you repeat, and it keeps on repeating. So we're gonna quickly start the lecture today, and then we have a Q&A in about 5 to 10 minutes, but I'll quickly start what about today. So computer vision is what I'm doing for my PhD, and it's basically teaching computers how to see. So handwritten digits is also a computer vision task, but it's I would say a trivial task now. So computer vision is used to understand the face detection, understanding medical images, particularly in healthcare. And the guest speaker today is one of the top researchers in AI applied to healthcare at Microsoft Research. And then self-driving cars, which Tesla, as people are more familiar with. So the car needs to see, it needs to understand what's happening around it. And this is what is driving compute. So how do computers see? So images are just numbers, as we've sort of explained before. And it's numbers between 0 and 255. And it's a grid, it's height by width. And if it's an RGB image, which is a color image, it's just 3 grids of the 3 grids of just numbers. So that is the important point I want you to understand, is that like all the so while we sort of have this very much semantic understanding of the world, like you know that this is a computer, this is a your phone, this is a Zoom link, you're on Zoom. All a computer is seeing is just numbers between 0 and 255. So to actually get a computer to map that to some higher level understanding, such as this is actually a face, this is a car, this is a house or a dog, is a non-trivial problem. And on a high level, what we want the computer to do is what we call high-level feature detection. So to understand what's happening in an image is that you can sort of like decompose it into what we call features or sort of concepts that describe this category. So for a human face, the eyes, the nose, the mouth. For a car, the headlights, the wheels, the license plate. For a house, the door, the windows, and the steps. So one way we could build a pipeline to sort of do computer vision is that we have some domain knowledge of what constitutes different types of objects. Then we define the key features which define those objects, and then we create detectors to detect those features in the images. But that is a very difficult way to do computer vision. Because one, if you could see, you have what we call illumination variation. So like you can't really explain to a computer that like, oh, like it has to be what we call invariant, or you should be able to predict that this is a cat on the different changes of illumination when it's occluded behind the grass, different variations of cat, when it's in the background, when it's deformed. So the difficult part of computer vision in particular is that you have all of these variations of the same semantic object, which in this case is a cat, and a computer must be able to predict that it's a cat under all of these transformations or changes. So what has transformed this field is deep learning. So instead of having to hand define to describe to a computer, this is how a cat looks like, we just collect a large collection of images, and then we train a deep learning model to classify these images. And what you end up seeing is that it's able to directly learn the features needed to classify objects directly from the data. So that is what is beautiful about this whole deep learning. This whole deep learning thing is that before, where we would have to sort of like hand define features, we just give these massive models large collection of images, and it learns the features that are important to recognize different sort of concepts and different sort of objects. And so before, we were looking at fully connected neural networks. And as you said, it's just layers of these perceptron units. Perceptron takes inputs, it weights the inputs and gives you an output. And this is what we looked at on the first day, and I just sort of went over in this, but on a high level, it's a similar thing we're going to do for learning from images. So the problem with these like fully connected perceptron units is that it doesn't factor in spatial information. So if you could recall, even though we have an image which is actually spatial, it has a height and width, and how these different pixels relate spatially is actually important to classify what is happening in the image. What we had to do for it to work for a normal neural network is we had to flatten it. So we basically remove the spatial information and we just flatten it into just a vector of pixels. So we want to avoid this problem with convolutional neural networks. And this is when you want to understand images. And another problem with these neural networks is that it has a ton of parameters. So if you look at this, every input is connected, every unit is connected to every unit of its input. So if an image is, say, for example, 1000 by 1000, you have basically 1000 input units, 1 million input units, and you have basically exponential growth in the number of weights in your neural network. And as we sort of alluded to, even if like having more weights could be detrimental because you sort of have more capacity, but that sort of overfits to the data and doesn't generalize as well as you want it to. So how convolutional neural networks are designed is that it actually captures spatial information directly. So it looks at an array of pixels as 2D images. So you actually do not flatten the image, and you look at basically spatial positions, and you connect the different patches. And a neuron, instead of seeing all of the units at a point in time, it just sees a patch of units. So for example, in this case, for the first hidden layer, this unit just looks at this small patch. Then the next unit just looks at this other small patch, and it just keeps on going until you fill out the first layer. And what we do is that we sort of share similar to like the recurrent neural networks, where we want to capture interdependencies across time. We want to share these parameters of the convolutional neural network so that it looks at different features across different parts of the input. So for example, if you detect an eye here, you want to be able to detect an eye here as well. So being able to capture this dependency, these sort of similar structures at different parts of the input is important. So that's why we share the parameters. And we are going to go through how this works in a little more detail after the next session. But now I would like to sort of welcome our Q&A speaker, Danielle. She is she's a top researcher at Microsoft in Cambridge in the UK. She's focused a lot on healthcare applications, and I'm excited to welcome her today.
Okay, thank you, Mandela, for that. So thanks, everyone. It's really amazing to see 190 participants. So what should I just present the slides I have, and then
yeah,
or do you prefer to jump into Q&A?
So you can present the slides first, to give people some context, and then so you should be able to share your screen, I believe. You should be able to share your screen.
Okay. Yeah. So that's it. All right. Can you see my slides?
Yep.
Oops. Let me see. Right. So, all right. So my name is Danielle Belgrave, and thank you for the kind introduction, Mandela. So today I'm going to talk about machine learning for personalized healthcare, which is most of what I do. Well, it's everything I do on a day-to-day basis. So I'm a principal research manager in Microsoft Research in Cambridge. I've been working in the healthcare intelligence team for the past 3 years. So a lot of the work I do is using these machine learning techniques to understand patient heterogeneity. And what does heterogeneity, why do we look at heterogeneity? Well, the phenomena we see in the healthcare setting is that we have patient groups, and we can think of patient groups as people with lung cancer or people with asthma. And what we notice is that people with the same diagnosis, receiving the same drugs, respond differently to different treatments. So understanding heterogeneity is all about understanding why do different people respond to treatment differently. So if you have 2 cancer patients, you give one the drug and they respond and they're fine, and you give another the drug and they don't respond, and not only do they don't respond, but they have adverse side effects as well. So they decline in health. Or you may have people who the drug works, but they have these really bad side effects. So we want to understand, why do different people have different reactions to drugs, and why do some respond and some don't respond to drugs? So this is a lot of what's underpinning most of my research, and I'm just going to present 2 examples that I've been working on. The first is understanding heterogeneity in asthma and allergy. So I'm working in the United Kingdom, and this was the study I did as part of my PhD thesis, looking at why people develop asthma and why people develop hay fever. So if you look at a lot of the medical literature, it says that if you have eczema, which is like an itchy rash in early life, you later develop wheeze, which is a type of asthma, and then you develop hay fever or rhinitis. And it's seen that these are causally linked. So using machine learning, we used hidden Markov models to try to condition what happens at one age on what happens at the previous age. So are these really causally linked? Or are they independent? And what we see is that if we look at the population today, anywhere in the world, we see that the profile of eczema, wheeze, and rhinitis, or hay fever, it follows this sort of profile where we see it looks as though they're causally linked. But when we use this hidden Markov model to disentangle this heterogeneity, what we see is actually on an individual level, only 3% of patients follow this sort of profile. The next problem and it's a problem I'm currently working on in Microsoft, looking at understanding heterogeneities in mental health. And mental health is an area that has huge impact on everyday lives. So the statistics say that 1 in 4 of us at some point in our lives will have a mental health condition. So a lot of us, we know people with mental health conditions, and very often it's hidden. And mental health is a very heterogeneous condition. Even if we look at conditions within mental health, such as depression or anxiety, they're very heterogeneous manifestations of what would work for different people with different types of depression or different types of anxiety. So this is a study I'm leading, collaborating with a group called Silver Cloud Health. And Silver Cloud Health is an online digital platform for people with symptoms of depression and anxiety. And it's an 8-week program that you take using something called cognitive behavioral therapy. So cognitive behavioral therapy is all about changing cycles of thoughts, feelings, and behaviors to stop things that could be harmful to our mental health. And the 3 areas we're looking at in terms of machine learning, firstly, ways of improving patients' engagement, because we know that the number one predictor of whether someone improves in their mental health outcomes is if they engage with therapy. The second is looking at ways to personalize interventions. How can we improve patient outcomes? And the third aspect of what we're looking at in machine learning models we're developing is more focused on NLP and looking at how we could upskill supporters. So understanding how language of therapists affects mental health behavior. So this is just based on some work we published last month using hidden Markov models again to understand modalities of engagement. So this is a model where our inputs, which are the whys, are actions people took. So you can take actions on different sections. So the platform of Silver Cloud has different modules and tools. And we looked at 12 different sections to see how engagement with those sections is related to patterns of engagement. And just at a high level, we identified 5 different patterns of engagement. So the high engagers, this group here, and then the low engagers who drop out quite quickly. And what we noticed is that the people who improve in their mental health outcomes, the PHQ is a measure of depression and GAD is a measure of anxiety. And there are 9 and 7 questions that you look at, and you look at it at different points during the program. And what we saw is that people who dropped out quite quickly actually improved the most. And this, I won't go into the details of the study, but this gave us an indication of it's not just how much you use the platform, but it's also the quality of your engagements as well. So take-home message in machine learning for healthcare, a lot of what I do is actually trying to understand the context. So context is really important in understanding machine learning for healthcare and really getting an idea of what is the clinical context to formulate models is really important. And this is what good science is about in the applied machine learning domain. It's about merging different schools of thought. So in Microsoft, I work with psychiatrists. Well, in Silver Cloud, they're psychiatrists and also designers. But within Microsoft, I also work with engineers and also with social scientists as well to help to understand the domain. And very much the approach that I use is very much problem-led. So trying to put patients and the person who's receiving interventions at the center of the study. So we use a data-driven approach, but also using domain knowledge for that. And that is it.
Sweet, thank you so much, Danielle. So I would sort of start with a couple of questions, and then I would leave it to sort of the audience to follow on. So I think it would be great to give people some context on sort of like your background, say growing up in Trinidad. How did you get interested in this sort of space? Were you always interested in AI? Was any mentors involved in sort of pushing you along certain directions? I think would be pretty helpful.
So I guess my interest in AI started with interest in mathematics. So when I was in school, so I went to St. Joseph Convent in Port of Spain, and it was really interesting to be in that environment where it was quite competitive in the sciences. And actually, my inspiration for going into math, so my undergraduate is in mathematics and statistics, and my inspiration was my math teacher. So I went to lessons with someone called Mr. Wallace, who'd been teaching for years and years. And he really inspired me to go down this route of studying math and statistics. And he's actually the one who inspired me as well to look at statistics in healthcare. So I remember he used to talk to me about working in clinical trials. And that for me was a great encouragement to have that sort of mentor in my life. And he really, he was amazing. And then when I went to London School of Economics, so that's where I did my degree, it was interesting because I always wanted to go into healthcare. So eventually I started, I did a master's in statistics, but focusing on healthcare applications. And then I think the interest in AI in itself started with looking at trying to broaden the impact of statistical and mathematical methods. So my background is not so much in the computer science side of machine learning, but more in the mathematics and statistics angle. And I think it reached a point where I realized that if you want to have impact in healthcare, you need methods, or impact in statistics or machine learning for healthcare, you need methods that scale. So this is what led me towards doing AI and more machine learning. So my PhD was focused on comparing statistical methods for healthcare settings with machine learning and trying to see, well, what can machine learning lend to the field of healthcare? And I think now working in tech, it's quite interesting, the potential of technology to impact healthcare. I think particularly in areas like mental health, where there's limited access to therapists, thinking of ways to scale solutions is what I'm really passionate about.
Got you. That's really exciting. I think I'll ask one more question before I move it towards the audience. Would you any sort of just like advice you would give to people who are sort of trying to get into the field? In terms of like, do you think having a certain background is important, or sort of like sort of this general advice of getting into the field? I think
so I think firstly, well, courses like this are fantastic, a fantastic introduction and overview of the field. And one of the things I really like about this sort of course is that it's very focused as well on theory, but also on practice. So if I could go back, I would do more competitions, go more into coding. So I think if you're interested in coding, code. And that's really great. But I think as well, in the field of machine learning and AI, there's a lot of scope for different talents. And AI is a very broad field, and also machine learning is a very broad field as well. So I encourage people to follow your interests and follow what you're passionate about, and try to see, well, how can your passions lead to solutions as well? Because it's really important that there's a lot of diversity of perspective in the machine learning field. So I think strong coding skills, good math is good as well, and also following your passions and learning your perspective as well.
Sweet. Thank you for that. And I'll move it to the questions from the audience. So there were a lot of interest about your studies. So people wanted some background on sort of hidden Markov models. If you could give like a simple overview, because we are not covering it in the sort of in the deep learning course. And then why was it suitable to solve that problem?
Okay, so this is a really good question. So I think I gave a very high level overview of the sort of models. So with hidden Markov models, this is really important in the sort of work I do. So it's maybe not the best way to solve every problem, but it's one way. And especially when we're looking at conditioning probabilities of events. So in the hidden Markov model, what we were doing was looking at the probability of a particular event and conditioning it on what happened just previously. So it's a series of probabilities that follow Markov properties, and the Markov property is a property of memorylessness. That you assume that the probability of observing a particular event at a particular time point is conditioned on what happens at the previous time point, and it doesn't matter what happens, all of the events that happens before that as well. So one of the motivations for doing this is to try to understand, so there are two things. One is using this hidden Markov model property, but also in the studies that I showed, I also included a latent variable that assumes that there was heterogeneity in how these probability transitions go over time. So we assume that there's a latent variable, and the latent variable is it's something that's hidden, and you assume that you don't directly observe this, but you can infer it from patterns of probabilities over time. So we can look at different distributions of that latent variable. So it was a discrete latent variable, and we looked at different prior distributions around that and assigned patients to each of those different groups. So that's a very quick summary of each of them.
Someone asked about does diet play a part of the inputs here? Example, in terms of acidic versus alkaline food intake, or would that be too expansive to add to the data set?
All right, that's an interesting question. So I guess, so for the particular, play a factor as well in a healthcare setting.
Sorry, you said that would play?
It could play, yeah, it could play, it could have an impact as well. And I think for both studies, looking at things like asthma, there is a known dietary effect. So in some previous studies, I have looked at the effect of different components of diet, of nutrition, and the impact on asthma. So this is a huge area of research, actually, but I've not looked at it within these particular models, but that's a really important area of research. I think there are challenges with measuring diets as well, and trying to understand nutrition. So it's usually very subjective based on people recalling diets as well. So, but it's an important thing as well to validate.
Got you. And then there was also questions about how do you go about collecting this data at this scale?
Right, through collaboration. So I've been lucky to have good collaborators and this is a great question, actually. This is a fantastic question because it's the most important part of doing these sorts of studies, where you, so look, a lot of work, putting on my statistical machine learning, my statistical hat, design of experiments and designing studies is the most important part of machine learning in healthcare. And because the data collection process is not trivial, data is very expensive to collect. So sometimes you have to make a compromise between what's available. But before you do machine learning studies or try to implement any sort of AI on this, on that's using a data-driven approach, a lot of times what you have to do is see, is there enough signal in the data to even start this study? or to start building models around that. So collecting data is not trivial at all, but I was lucky that I had good collaborators that had previously existing data. The other thing is, like, for the mental health study, having data at scale is helpful as well. So if you have enough data, many times you don't have to worry so much about design, but you do still have to be aware of good design principles for machine learning for healthcare.
There was also some questions on there seems to be a sense of people trying to get a sense of like how, say, fully reliable these models are. Like, can it sort of like replace the input from a psychiatrist, or can it be used to predict certain patient behavior without sort of like human input, or which part of the pipeline in the human computer interface is this being used?
Yeah, very interesting question. So I think one of the big advantages of using AI and machine learning in this sort of domain is the scale of the data that you're looking at. So and being able to create models that can make predictions quickly. So for the example of the mental health data, what we were looking at there was 1,000 different engagements, 1,000 different things you could do on the platform, so 1,000 different units of engagement. And this is a lot for a human person to process and to try to identify patterns. So the advantage of using AI is identifying patterns in a scalable manner and sort of making the human therapists work a lot easier by recognizing patterns quickly, so that they can that they can carry on their function of work. So I think there is a big role, especially in these very large data settings. There are other settings in the machine learning for healthcare fields as well. So, for example, where you have to make decisions. So I'm very much an advocate of a human-centric approach to machine learning for healthcare. I think this is really important. And I think as well, machine learning and AI can augment human decisions as well and help people to make decisions. So an example is in an ICU setting. So some of my colleagues at Microsoft are working on intensive care units and trying to see, well, what would an AI or machine learning algorithm propose a different solution to a doctor when you're prioritizing beds, or when you're prioritizing who to give different interventions to. But at the same time, I think the final decision has to be the human in these sorts of settings.
Got you. And then I think one or two more questions was around how do you deal with sort of the diversity of humans, and like how do you factor in sort of like everyone is sort of different, and do these models capture this sort of the human diversity?
So that's a big motivation of what I do. This whole idea that not everybody responds to treatments in the same way, and the hidden Markov models, combining the hidden Markov models with these latent variable encodings to identify what are these heterogeneous patterns in symptoms, is a good way for us to identify types of diversity, at least diversity on the clinical manifestation level, and how we could encode that. Does that answer the question?
Yeah, I think it does. And then people wanted some more practical questions of math versus computer science degree. Like, does it really matter from your experience for people interested in getting into the field?
Yeah, so I think my opinion is helpful. And I think it's important to have people engineers, and those engineers okay, I think something went wrong with my internet.
Yeah, I think you dropped for a little bit.
Yeah, I just had to, so something went, so I think it's about people following what their preference is a little bit. So for example, in my team, I work with engineers and researchers as well, machine learning researchers as well. So engineers the engineers in my group tend to have more of a computer science background. I have more of a mathematics background, and there's someone else who has a physics background, actually. So there are different routes for getting into machine learning and AI. Actually, a lot of people in the lab who are in machine learning are theoretical physicists. So I think all skill sets are good to have, and it's important to have strong skills. And I don't think I don't know what other people think, but I don't think it matters so much what your degree is. But I think it's really important to build up strong quantitative skills and really strong coding skills as well, good engineering practices and good programming as well, independent of what degree.
Got you. And then the last question was around the sort of building off of that, having sort of different perspectives. How do you all incorporate, say, theories or perspectives from, say, like a pure medical or psychological perspective when developing these AI statistical models?
Good question. So I think working in an applied domain, it's a lot about communication, actually. So sometimes it's hard and sometimes it's easy to try, because you have people with very strong discipline, they're very strong in their area of discipline, and it's about trying to translate between different disciplines as well. So for example, me talking to a clinician, I have to elicit from them questions that are challenging enough for machine learning, and thinking, well, why do we need machine learning to solve these problems? So it's up to me to communicate what machine learning is and what is the potential of machine learning, and also to elicit from them questions. So I think communication is key here. The other thing, so one like really practical thing that I like to work with in particular is every time I work with a clinician, one way I try to sort of get this knowledge on so that we're all on the same page is by working with them through domain graphs. So I use domain knowledge graphs, and usually what I do if I'm working in a new area, I try to ask them to map out to work with me to map out a graphical model of how they think this would be represented graphically. So that's just a really practical exercise that I use personally to try to get them thinking from a machine learning perspective, try to get them thinking about causality and other concepts within machine learning. And also for me to try to understand their language in my language as well.
Actually, one last question. So people are curious about sort of the realities or experiences of being a woman in STEM, particularly in a male-dominated field such as AI. How has your experience been, and sort of like, do you have any advice of sort of like women interested in sort of the field of STEM and AI machine learning?
So I'm gonna give two answers. So I must say that I count myself as quite lucky to have grown up in Trinidad, because I think this was never a problem in Trinidad, to be honest. That I never felt as though being a woman in STEM sort of was a differentiator or anything, but rather, I think this has a lot to do with, I don't know, that's just my perspective. Whereas maybe when I moved out of Trinidad, I did see a lot more that there was a lot more inequality in educational systems. So just my personal perspective is I feel very grateful. I don't know whether after secondary school it would have been different in Trinidad, but my perspective was that I was really grateful to the education system within Trinidad, actually, for really empowering women in science. But that could be just my context, that I went to an all-girls secondary school, but even in primary school, I was in a mixed school, and there was a lot of equality. I think it's very important for anyone, but for women in STEM as well, to have allies and to really have people within the fields that you that you trust as well. And this is one thing that, as a woman from an ethnic minority, or not minority, an underrepresented group in machine learning, I must say that this is something that I'm very grateful for. That that you can find allies and people who have your back, so that you can get on with doing good research. So this is really important. I think events like this as well, forming networks as well, forming networks of people who are diverse, who are different to you, who have different perspectives, who come from different backgrounds as well, is super important, and it's super enriching as well. And I think this is a way that we can all champion each other. So it's not just, I think as women in STEM, we shouldn't feel that we're responsible for sort of championing women in STEM, but also I think that everybody has this responsibility for championing each other when people are doing good work.
Sweet, thank you. And any parting words for the audience?
Well, thank you very much. I've been looking at the questions at the side, and it's really interesting as well. And it's really exciting to be able to talk here. And thank you so much, Mandela, for all of the work you've put in organizing this. This is great stuff.
Thank you, thank you. So yeah, we all appreciate you taking your time, Danielle.
Thank you for having me.
Loved your insights and experience, so really appreciate it.
Okay, cool.
And people are asking for any contact information if you have as well.
Yeah, okay. So I can put my email address. Okay, great. Good. Okay, thank you so much.
Thank you so much, Danielle. Have a good one. All right.
All right, take care. Bye.
Perfect. Hope you all enjoyed that session. We're gonna sort of move back swiftly into the presentation. So I'm gonna share my screen again one more time. So yes, we were talking about convolutions. So the important thing to sort of understand, and also please feel free to post questions in the chat as you sort of encounter. So the main point is that you want to be able to recognize concepts in irrespective of deformations. So even though these are both sort of X's, the one to the right is a little more deformed X. And we want the model to be able to predict it being an X no matter what the deformations is. But as you can fundamentally see, they have similar features. They have basically the middle X, they have the sort of features on the diagonals. So fundamentally they share similar features. For people ask about the contact information, I think she made a mistake and just posted it in the panelist. So I'll just post it in the main chat. To detect X features, we want to look for these smaller features here. So we want the stuff we want this one, we want the middle one, and we want the ones on the other ones on the edges. So basically what a convolution is that it's basically like a little patch that we sort of compare how similar the patch is to the input. And if the patch and the input are similar, when you multiply the two together, we get a very high value. And if it's not similar, we get a very low value. So in this case, if we do element-wise multiplication. So we multiply this one by this one, 1 by -1, 1 by -1, and we basically do element-wise multiplication and we add it up. And this is all a convolution operation is. You just do patch-wise multiplication, element-wise multiplication, we add it up and apply the nonlinearity. So let's walk through an example here. So this is our image, which in this case is just zeros and ones. We have our weight matrix, which we describe as a filter. And all we do is we apply it right here. And then we keep going on the line. So we multiply this filter by this image, this part of the image. 1 by 1 is 1. 1 by 0 is 0. 1 by 1 is 1. And we multiply each element by each element. We add it up and we get 4. Then we shift it 1 position to the right. We do the same thing again. 1 more position to the right. We shift it again. And essentially, we keep shifting it until we have gone over the entire image. And essentially, different filters essentially capture different features. So for example, if we have this, what we call a sharpen filter, it sharpens this original image. If, for example, we have an edge detector, it finds the edges, and a strong edge detector finds stronger edges. So the important thing I want for you all to get is that filters basically are like feature finders, right? They find different features of the input, and they sort of, so in this case, it might sharpen, edge detect, etc. So all convolution is that we apply these filters and we slide it over the input. And essentially these filters sort of represent different sort of features, and if there is high similarity between the filter and the input, the output is high, meaning that there's a good match. If it's low, it's a bad match. And we pass the same filters over all parts of the input because we want to capture the same features irrespective of where the feature is, irrespective of where the concept is in the input image. So if we see an eye here and we see an eye here, we want to be able to identify the eye no matter where it is in the image. And so all a convolutional neural network is basically just these convolutional layers. So before where we would have like what we call linear layers, that we looked at in this notebook, we looked at linear layers. We're going to look at convolutional layers, which are essentially just looks at patches instead of looks at the flattened input. Then we have what we call pooling and a nonlinearity. And this just goes into sort of the specific math details. For all you're doing is just essentially just doing as I described before. You multiply the filter by the patch, you add it up, and that's pretty much it. And we looked at the nonlinearity before. In this case, we're looking at the ReLU, and you apply it after the convolutional layer. Similarly, when you apply it after the linear layer. And then pooling, all pooling does is looks at a patch and finds the maximum value. So in this case, in this patch, the maximum value is 20. In this patch is 30. In this patch is 112, and in this patch it's 37. So if you look at the convolutional neural, it's fundamentally pretty simple. It takes an input, it applies a convolution, and all the convolution does, it looks at different patches, element-wise multiply, sums it up. You have multiple of these filters. Then you apply pooling. All pooling does, it looks at patches and finds the maximum value. And then you have the same multi-layer perceptron as we looked at before, and that an output layer, which tells you what class the output image is. So fundamentally, if like all we have changed right now is that we've replaced essentially all of these linear layers with convolutional and pooling layers. And this is better able to capture the spatial structure of the image. So similarly to like recurrent neural networks, where we want to capture the temporal aspect of sequence data. So we had sort of this like repeating recurrent units. In this case, we want to capture the spatial aspect of images. So we have these convolutional units which capture spatial information in patches. And what So the purpose of pooling is sort of one, to downsample the data. So for example, for computational reasons. So if you, in this case, the image is 4x4. After we pool it, it's 2x2. So it's one computationally it's computationally more efficient. And also it allows you to sort of capture the important feature, if that makes sense. So the fact that you sort of max pool means that the most important value sort of save for further processing, meaning that you want to capture the most discriminative part of the input. So let's stop here for a little bit. Do people get, so let me poll the audience. So if you sort of get the difference between convolutional neural network and the sort of vanilla neural network we look at on Monday, type yes. If not, click no. So CNN stands for convolutional neural network. Sweet. For most part, people seem to get it, which is good. For a quick overview again, the main problem with these vanilla neural networks is that you have to flatten the input, and that works for certain types of data, but particularly for images, if you flatten the input, it no longer has a spatial information, and spatial information is very important for image understanding. So what we do is replace all of these, what we call linear or multi-layer perceptron layers, with convolutional layers. And all a convolutional layer is that it looks at small patches of the input, and essentially what the operation does is that it's looking for maximum similarity between the filter and the little patch. And if it's a high overlap, the value is high. If it's a low overlap, the value is low. And yep. And then pooling, it's pretty simple as well. You just take the maximum value. And one last thing I would like to explain is that for one filter, you get one layer. So filters are initially randomly initialized. You could sort of define specific filters depending on what your task is. So for example, here we could define a specific sharpen filter, because if you multiply any sort of numbers by these numbers, it sharpens the image. But what happens is that we eventually learn the values of these filters, which is what I was going to show you here, is that these filters are eventually learned when you train the neural network. So it learns to capture different important features to detect in the image. So here, it's a hierarchy of features. So you have edges, then you have mid-level features, which is eyes, ears, nose, and it composes these mid-level features to get high-level features. So as we said, similar to like similarly to like the vanilla neural network, right? Remember, when we first start off, it doesn't know how to do anything. It's pretty much stupid. You need to give it some data and some labels, and it's able to associate the data with the labels, right? And eventually it learns the weights of this neural network to do well at the task. Similarly, when a convolutional neural network by itself cannot do anything. It's just stupid at the beginning, but you give it a bunch of input data and the correct label, and eventually it learns the weights to understand the input to map to the output. In this case, because we're looking at image data, the weights are like these little images and these little filters, and these filters captures important features that are important to learn to understand the input. Does that make sense? Yes, in the chat before we move on. Sweet. So yes, you have the input image, convolution, layers, pooling, and then you just repeat this stuff. And Then you have your output layer like before, which applies to each class. So say if you have 10 classes, we have 10 outputs: car, truck, van. And this ACTIC is used for a bunch of applications. So breast cancer screening, so along the healthcare lines that Daniel was talking about, we could use it for semantic segmentation. And a ton of, so fashion detection, robotics, self-driving cars, face detection, you name it. This is all powered by convolutional neural networks. So as Carmel just asked, is this how Google Photos recognizes similar faces and groups them together? Yes, all of these stuff are driven by convolutional neural networks, particularly convolutional because it best captures the spatial aspect of images. So facial detection, robotics, self-driving cars, facial detection, Amazon product recommendations. These are all literally built using these foundational concepts that you have learned today. Like obviously these stuff are training a lot more data. They are optimized so that they work really well, but the fundamental concept is they use convolutional operations, pooling operations, and linear layers with non-linearities. That is the main takeaway. Convolutional layer, pooling, fully connected layer, and non-linearity. So now let's go on to the coding exercise. I will post it into the chat now. And what you all will see is that the structure is very similar to what we looked at earlier in the week. And so let me know if you all can access this. If there's any problems, don't forget, save a copy in Drive and change the notebook settings. And need to request access. Okay, sorry. All right, sorry, updated, sorry, new link. Sorry about that. So use the link I just posted. I got a ton of requests. This should work now. If not, let me know. All right, sweet. Yeah, so this is a convolutional neural network here. As we said, it takes an image, applies convolutional operations, it gives you some feature maps, you apply some pooling, and then you do the same thing again and again and again. So similarly as before, so y'all could go through this with me as I go through it. So as when you all save a copy in Drive, can you all post ready if you're ready to go through the notebook? Perfect. So here, the first cell is some imports. You don't need to go into all of the details, but we need to import some convenience functions to make our lives easier. In particular, what is convenient about this notebook is that we're using this library called Torch Vision, which is a branch of PyTorch, which is a library from PyTorch that has a bunch of data sets already packaged for you. So for example, we are going to use the MNIST data set again, but you don't have to define your data set as before. It does that for you already, which is convenient. So here we set some seeds. The random seeds basically allows you to sort of guarantee some deterministic access, deterministic running of the program. Because if you do not set your seed, it's you cannot replicate the same result. So you set the C to sort of make the program run deterministic, particularly for random applications. And here, so let's look at the filters again. So here we have a 2x2 filter, and we look at a 2x2 input. So we multi-element wise multiply, we add it, and that gives us an output in green. And when we do that, we keep sliding this filter across the entire image. And eventually we get this convolved output. Similarly, it's the same. So here, so as we keep sliding this, it basically gives you the output in green. And this is the eventual output of the applying the filter. And in this case, it focuses on the edge of white into black, right? So this Noble does a really good job of explaining convolutions. I'm not going to go over it right now because we sort of already go over it. But when you go over the notebook, you can take your time and essentially fully understand what the convolutions are doing, and it does a very good job of explaining different of the filters, etc. So let's let's skip CNN basics because y'all can go through that sort of later tonight. So let's go to the load data section. And here it's the same thing as we did before. So we want to we change the run, let me make sure. Right, we have the GPU, make sure your GPU is on. So you go to edit, notebook settings, and GPU. And here you're setting the device that you want to work on. So if you have CUDA available, meaning you have a GPU available, the device is CUDA or GPU, else it is the CPU. So you run that. And watch how beautiful this is. So before, where you would have to, in one, have to define your own data set, where you would have to sort of define, you'd have to download the data set first, then you would have to load it from disk, and then define how it is sort of, how you want to package the data. When you import Torch Vision datasets as datasets, you could use the built-in MNIST dataset. So all you do is do datasets.mnist, you pass in where you want to save the data, it automatically downloads it to this root directory. You specify which partition. So here you want the training data, and you specify that you want to download it. So just run the cell, and it does the downloading and extracting for you. Everyone's good. So the next thing we need to define is our transformations. So what transformations does is just basically add some randomness to the input, so that essentially it's a way of we call data augmentation. So that basically, remember, recall that we want our model to be invariant to nuisance factors. Invariant meaning it needs to be able to still predict that it is a cat if the color changes, if it has background clutter. So essentially, data augmentations or transformations are a way for you to essentially add random crops, add random rotations, and to normalize the data, because data needs to be normalized for a neural network to work well. So we just need to run this cell. This would eventually transform the data. Here we load our training data. So train equal to true. Here testing data, train is equal to false. We download it, and then the transformation that we apply is the train transformation, and then the testing transformation. Right? We're all good. And then we also want to split our training data into validation. So we take 90% of the training data, and we use that as validation. So we randomly split the training data into training data and validation data. Here, we apply the transform of the validation data to the same thing as the test. And we print the number of examples, and then watch this. This is the same thing we did last time, right? So we define a data loader, which specifies how much examples we want to look at in a batch. So remember, we recall that we have the data loader. It takes in a data set, the batch size, and you want to shuffle it during training, or you don't want to shuffle it during testing. It doesn't matter whether you shuffle during testing, but during training, you have to shuffle so that it is random. You want some level of randomness, otherwise the neural network just cheats and overfits to the data in the mini batch. So let's run that. And let's stop here. Does this make sense so far? Please put yes in the chat, no otherwise. So this is very similar to what we did on Monday, except that you no longer have to define your own data set. It does this, it downloads and defines the set for you automatically with Torch Vision. And then we have to define our data loader, which specifies how we want to group the data. And right? And then similarly, like last time, we need, what do we need? We need a model, right? We need to create our neural network model. So here we define our model. So before, when we had a layer would be a, instead of a linear layer, we want to use a convolutional layer, which is defined as conv2D. So question about larger or smaller batch size. So this is something we briefly covered on the first day. Recall that we looked at gradient descent. So in normal gradient descent, you look at all of the data at once. So if your data set size is 1,000 examples, you take the gradient of 1,000 examples at once and you update the weights given that 1,000 examples. But the problem is, as your data set size grows, it's impossible to computationally compute gradients on that large amount of data. It just takes forever. So the alternative is you could just use one data point and compute the gradient of one data point. So that's batch size equal to 1. But that is pretty noisy because you're basically, it's like you're basically determining where to go just based on one data point, which is probably not sufficient. It's like if you sort of just like go into the exam by just looking at, by just practicing on one problem. So the best of both worlds is what we call mini batch gradient descent. So we take a batch size of say like 64, and we take 64 data points at a time. We pass it into the model, and then based on that gradient, we update the parameters. Right. So in channels, so for convolutional layer, it's the in channels, which is basically the number of, so an image is composed of usually 3 channels. So we have red, green, and black. It's, yeah, so yeah, image is usually composed of 3 channels, but for, since we're using the MNIST data set, which is just all grayscale images, we use number of input channels equal to number of input channels equal to 1. And then out channels is basically number of filters we want. So basically a filter looks at a particular feature. So for example, we have out channels equal to the number of filters in that layer. And then kernel size specifies the number, how big the filter is. So in this case, the filter is 2 by 2. A 5 by 5 filter will be 5 by 5, 5 and 5, and it looks 5 by 5 input in the image. And then we have another convolutional layer. It takes now 6 channels because we had output 6 here. Then we have 16 output channels, and we use the same kernel size 5. Again, these parameters is what you set. Like it is an art of picking these values, and you have to just basically try a bunch, but the structure is pretty much the same. And the size of the filter defines how big of the spatial region you're looking at. So if it's only 2 by 2, you look at only a 2 by 2 region. If it's 5 by 5, you look at a bigger region. So yeah, and then it's the same thing. We take an input X, this is the image. We apply the first convolutional layer. We max pool. Remember max pool, all max pool does, it takes the maximum value in a 2 by 2 grid. In this case, the grid is 2 by 2 because the kernel size is 2. We apply a nonlinearity, which is a ReLU function. Then we do the same thing again. We pass it through the second layer, apply max pool, we apply ReLU. And then this is the sort of, if we go back to this, so I'm trying to see if I can map a theory to the thing, to the coding, is that after you apply convolution plus ReLU plus pooling, we do a few layers of those. We have what we call the classification head, which basically takes the feature map and then outputs the score. So we need to flatten it. We need to flatten it, and then we apply as many other normal perceptron layers as before, and then we have a final output layer, which basically is equal to the number of classes we have in the data set. So here we flatten it. So basically -1 means we flatten it and we keep the batch size. Then we apply the first linear layer, the first linear layer. So the linear layer, so this is a flattened output. It takes the flattened output and outputs 120 units. Then the next fully connected layer takes 120 units and outputs 84 units. And the last layer takes 84 units and outputs the size of the number of classes, which in this case is 10 because we have 10 images. And that's pretty much it. Is this clear? Is the model clear? Please put it in the chat. So all we've pretty much done is replaced the linear layer from the first day and replaced it with convolutional layers. And what you would see is that we got like about 81%, I think, on the first day. We're pretty much going to get about 99% with these convolutional layers because it better captures the spatial structure of images. And it's very simple. You define your layers and then you define how you compose them. You apply convolution, you apply max pool, nonlinearity, and you keep doing it again. And I encourage you all to play with this, play with these parameters, see how as you play with this, the values change, etc. But getting comfortable with this stuff is a matter of just spending the time. And it will eventually come, but it's just like once you understand the high level concept of what's going on, it hopefully will become much clearer. So similarly as before, as in notebook 1, we have to define our optimizer. We're using the same SGD optimizer. Well, actually, no, we're using the Adam optimizer here. So Adam is all right, we create our model, we move it to GPU. And as you said, we have an output dimension of 10 corresponding to the number of classes. All right. So again, Adam optimizer. So here we're using the Adam optimizer. It's the standard now. Here we use the SGD optimizer. Like the specifics of the optimizer isn't too necessary right now as you're learning this stuff. But these optimizers define how we sort of use the gradients to optimize the weight of the parameters. And some are better than others. Adam is now the sort of de facto one. So we're just using the Adam optimizer with the default learning rate values. And again, we have a loss function. We're using the same cross entropy loss because we're trying to compare probability distributions. It's the same thing. So is everyone up to here at number 5? Can they get it to run? Please in the chat, yes. If it's clear, if they're starting to get the sort of pattern of how this is, how this is working. Sweet. And look at this again. So this is the training loop, and it's the same thing, right? We have to use the iterator, which is the data loader. We put it on the GPU. The X is the data, the Y is the label. We zero out any gradients before we run it through the model. We pass the data into the model. It gives us its prediction. We get a difference between what it's predicted and what the actual ground truth is. Here we calculate the accuracy. We calculate the gradient. We update the weights, and we keep doing that. And then we also have an evaluation loop, which measures the performance on the validation set. So we calculate the loss and accuracy on the validation set, but the code is pretty much the same. There isn't any difference. It's just the data that you're validating on. So, all right. So guys, so I want everyone to run this and verify that you get about 98, 99% accuracy. So it's gonna take maybe like 3 or 4 minutes. Runtime for CNN is longer because for this one, it has more parameters. So here, as you can see, the training accuracy. So the loss starts off at 0.415. So remember, we want the loss to decrease, right? Remember that we want the loss from the first lecture. We want to get to the bottom here. So we start off pretty high. The loss starts off pretty high, but we eventually want the loss to drop until it converges. If you're getting an error, it's probably because you missed running a cell above. So verify that you run all of the cells above. You shouldn't be getting an error from what I've seen. So you see here, we want the loss, the training loss to decrease, and we want the validation loss to also decrease as well, until eventually it starts overfitting, and then the loss of the validation starts to increase. So let's look at this, right? So the loss starts at 0.415, it drops to 0.146, it gets lower at epoch 3, and then it drops to 0.084. As you can see, the validation loss is also decreasing as well. That's a good sign. And then it takes about, what, 20 seconds per epoch. So about 2 minutes to train. And then eventually, the validation loss also decreases, continues decreasing. The train loss also decreases. And you get a validation accuracy of about 98.60%. And then we test it on the testing data, and then the testing accuracy is 98.67%. Is that clear? So this post in the chat, yes, this makes sense. No, this doesn't. Perfect. So everyone, like, if you could go through this notebook and understand everything for the most part, and then also the one we went through today on convolutional neural networks, this is a success. So go through these 2 notebooks again tonight. See whether this makes sense. If there's any questions, shoot it over. But if you'll understand, it's just 5 main things you need to get. It's load the data, define the model, and the main layers in the model is linear layers and convolutional layers. You need to define your optimizer, which says how you want to change the weights. You need to define your loss function, define your training loop, and then you run the training loop for a certain number of epochs, and your model trains. So there's a question about overfitting. So overfitting is one of the biggest problem with machine learning. So essentially you have training data, but what you want to train the model, but what you want to use the model for is on some testing data that you have never seen before. If you just learn the statistics of the training data, say if you get 100% accuracy on the training data, the training data might not be fully representative of what you would be testing on. So that's the problem of overfitting, where you sort of overfitted the training data, but you don't generalize well because you sort of just learn the sort of noise in the data rather than the actual underlying structure. With changing the channel, input and output channel give you a better accuracy. It depends. You have to, so you could try it yourself. So all you could, so to try, people who want to experiment, and I encourage you all to experiment with it. So you all could, so yeah, so you'd have to, if you change the output channels here, you would have to also change the input channels here. And then if you change the output channels here, you'd have to change the linear layer here, like the units of the linear layer, the input units of the linear layer. And yes, you can, so you can add more linear layers, you can add more convolutional layers, as you please. And I encourage you to play with it. You probably might get errors the first time you try it around because you have dimension mismatch. And if you could debug it yourself, that means you understand how these dimensions work. But yes, you could change these stuff. These are all, as I said, hyperparameters that you sort of play with. Yes, the slides would be posted on the website. And then the last thing I will show you all for today, I think this was developed at my group at Facebook. It's object detection, and I will share the slides as well. The recordings are posted on the website for people who have been asking. Everything is on the website. It gets posted at the end of the day. So if you go to the schedule, you see slides, video, coding exercises, and slides, video, coding exercises. And today will be posted at the end of the day, at some point today. So yes, object detection. So classification is assigning a label to the image. Object detection is basically drawing a bounding box over the image. So this, I wouldn't run through this notebook right at the moment, but I would encourage you all. It's very simple. You just keep on pressing play to see the output, but I could give you a sample output to show you how it looks. So yep. So yes, so this is, this is what we call semantic segmentation. So given an image, we want to segment it out into semantic categories. So before, with image classification, we just want to assign a high level label. In this case, we have multiple objects and multiple semantic categories, and we want to be able to segment out the different semantic categories in an image. So this is an important task for self-driving cars, to understand what is happening around it. And in this case, it's able to segment these into cars, traffic lights, buildings, sky, person, fence, etc. And yes, object detection is exciting for people to see it again. I could run it again. But when you run through the notebook, it would also output this for you. This is just the final output. But yes, it's, and the fundamental thing is this, what's the model that is being used for object detection is the same convolutional neural network. So to give you a sense, so before, this is what we call a neural network backbone, and it's fundamentally it's learning the features, like this is the eye, etc. And then for classification, we use a classification head. But we could replace this part and then use it for object detection and semantic segmentation, which is basically, yes, trying to segment out parts of the image. So the important point I'm trying to get across is that the stuff that you learned today is basically the foundational stuff of what is being used for self-driving cars, and to understand sort of the world around us, facial detection, medical imaging, etc. And if you all play with the notebook I sent, you all will be able to see some of these results. It uses this library developed at Facebook called Detection2, which basically has a bunch of what we call pre-trained models, and you can just give it the input video or input image, and it automatically can segment it for you. So you could play with that for those who are more advanced and want to sort of, yes, play with object detection. Any questions? Does everything make sense? Give me a final sweet. Yeah, so please, I urge everyone to go through Notebook 1 and particularly 3A again. But those who want to get into RNNs, it also, Notebook 2A is also good, but I think 1 and 3A is probably the most important ones to get your hands wet on what's happening. But yes, for the people who are struggling, don't worry about it. It takes time, like, and particularly if you didn't have a coding background, just getting used to Python syntax is also another hurdle you have to jump through. But hopefully you get the high level concept. Once you keep playing with it enough, hopefully you'll be able to get it. And I'll see you all tomorrow, where we'll be talking about deep generative modeling, which is probably one of the most exciting branches of AI at the moment. I thank you.